Hello everyone, here is a question based on molar conductivity. The resistivity of a 0.8 molar solution of an electrolyte is 5 times 10 to the power minus 3 ohm centimeter. Its molar conductivity is how much? We have to find out the answer in terms of 10 to the power 4 and we have to find out the nearest integer. This is not a difficult question to solve, but if we are not careful about the unit conversion, then there are chances of making a mistake. So we know that molar conductivity, that is lambda m, is equal to specific conductance, that is kappa, divided by concentration, that is expressed in molarity. Here specific conductance is not given, but the resistivity is given, and we know that specific conductance is equal to 1 by rho. Rho value is what given here, 5 times 10 to the power minus 3 ohm centimeter. That's what given here. So therefore molar conductivity is equal to 1 by rho times molarity. So therefore this is equal to 1 by 5 times 10 to the power minus 3 ohm centimeter. Molarity is given as 0.8 molar. So 0.8 mole per liter. Now let us first convert this per liter to per meter cube. Then we will convert this per meter cube into per centimeter cube so that we can cancel the units. So that's the tricky part here. Per liter is equal to 10 to the power 3 per meter cube. How? So 1000 liter is 1 meter cube. So 10 to the power 3 liter is equal to 1 meter cube. If it is per liter, then we have to put minus everywhere. So therefore 10 to the power minus 3 per liter is equal to per meter cube. So therefore per liter is equal to per meter cube divided by 10 to the power minus 3. When this goes up, it would become 10 to the power plus 3. So that's what I have written here. Now if we substitute this one first, then what will happen? This will be 1 by 5 times 0.8 is 4, isn't it? 8 times 5 is 40. So that means we have 0.8. So therefore it is simply 4 times 10 to the power minus 3 ohm centimeter. Let us first put this value, 10 to the power 3 per meter cube. Now we know that 1 meter is equal to 100 centimeter. So therefore we can write it this way, 10 to the power 2 centimeter. If we are writing it in per meter, then it will be 10 to the power minus 2 per centimeter. So if we are cubing it on both sides, then it would become 10 to the power minus 6 per centimeter cube, isn't it? Because we are basically cubing x to the power a to the whole power b, we can write it as x to the power a times b. So if we have 10 to the power minus 2 to the whole cube, then that would become 10 to the power minus 6. That's what I have written here. So now for this per meter cube, let's substitute this value. If we do that, then 1 by 4 we can write it as 0.25, isn't it? And this will cancel. So let's send this one up, per ohm per centimeter. This one, if we are sending it up, then that would become 10 to the power plus 6 centimeter cube. So we can cancel this and that would become centimeter square. So what we have is 0.25 per ohm times 10 to the power 6, we forgot the mole, So we have mole here, 10 to the power 6 centimeter square per mole, which we can write it as 25 times 10 to the power 4 per ohm centimeter square per mole. So 25 is the correct answer here. The quantity of electricity in Faraday needed to reduce 1 mole of dichromate ion to chromium 3 plus is how much? We know that charge of 1 mole of electrons is what we call it as 1 Faraday, because charge of a single electron is equal to 1.602 times 10 to the power minus 19 coulomb. So therefore that value multiplied by Avogadro number is what? The charge of 1 mole of electrons. So therefore charge of 1 mole of electrons is equal to 1.602 times 10 to the power minus 19 coulomb times Avogadro number, that is 6.022 times 10 to the power 23 per mole. This one will be approximately 96,500 coulomb per mole, and that is what we call it as 1 Faraday. Now here in the dichromate ion, we first need to see the oxidation state of chromium. So therefore let us keep it as 2x, because we have 2 chromium atoms, plus 7 times minus 2, because valency of oxygen is 2, therefore the charge we give it as minus 2, and that is equal to minus 2 because the net charge is 2 minus. Therefore 2x minus 14 is equal to minus 2. So therefore 2x is equal to plus 12. Therefore x is equal to plus 6. Chromium is in plus 6 oxidation state in the dichromate ion. So it is undergoing reduction and becoming chromium 3 plus. But when we have 1 mole of dichromate ion, how many moles of chromium 3 plus we will get? We will get 2 moles, isn't it? Otherwise the equation is not balanced. So therefore for 1 mole, how many moles of electrons are required? That means we require 6 moles of electrons, isn't it? Because we have to multiply with the 6 moles of electrons, not 3 moles of electrons. Because if you multiply with the 3 moles of electrons, then we cannot get 2 times chromium 3 plus. At that time we have to write only chromium 3 plus, 1 times chromium 3 plus. So therefore the correct answer is 6 moles of electrons. Therefore 6 is the correct answer here. That means 6 Faraday. For the given reactions, the electrode potentials are given, tin 2 plus becoming tin and tin 4 plus becoming tin. The magnitude of standard electrode potential for tin 4 plus becoming tin 2 plus is how much? We have to find out the answer in terms of 10 to the power minus 2 volt. So if it becomes negative, then we have to change the sign, but if the value comes positive, we are going to keep it as it is. And we know that delta G standard is equal to minus NF E cell standard. Based on the equations given, we are going to write 2 equations. One is delta G1 standard is equal to minus 2, because 2 electrons are involved, times Faraday constant times E cell standard value is given as minus 0.140 volt. So therefore minus 0.140, and that would be equal to 0.280 Faraday. And then delta Z2 standard is equal to minus 4 Faraday, because 4 moles of electrons are involved, times E cell standard, that is 0.010. Therefore this is equal to minus 0.040 Faraday. Let's say this is equation 1 and this is equation 2. Let us subtract equation 1 from equation 2. In that case we can write that tin 4 plus 4 electron minus tin 2 plus minus 2 electron. On the right hand side it would be 0, but then this would become 2 electron. So therefore let us send tin 2 plus this side. So therefore tin 4 plus gaining 2 electrons becoming tin 2 plus. So therefore delta G3 standard is equal to delta G2 standard, that is minus 0.040 Faraday, and then again minus because we have a minus sign in the equation, 0.280 Faraday. So therefore minus 2 times Faraday times E cell standard, because here also it involves 2 moles of electrons, that is why 2 here, is equal to minus 0.32 Faraday. So Faraday constant is common on both sides, therefore we can cancel that. Minus sign is also common on both sides, we can cancel that. So therefore E cell standard is equal to 0.32 divided by 2, and that would be 0.16, which we can write it as 16 times 10 to the power minus 2 volt. So therefore 16 is the correct answer here. The cell potential for the following electrochemical cell is given as 0.801 volt at 298 Kelvin. The reaction quotient for the above reaction is given as 10 to the power minus 2. In that case, what is the number of electrons involved in the given electrochemical cell reaction is? Standard reduction potential values are given. The reason why I am saying they are reduction potentials is because zinc 2 plus has to gain 2 electrons, then only it can become zinc. Likewise, tin X plus, we have to find out the X value here, has to gain X number of electrons so that it can become tin. So therefore standard reduction potential values are given, and this is the value we use in the Nernst equation. We know that Nernst equation is E cell is equal to E cell standard minus 2.303 RT by NF log Q. Q value is given as 10 to the power minus 2, and we know that E cell standard is equal to standard reduction potential of the cathode minus standard reduction potential of the anode. Now here, which one is anode, which one is cathode? Obviously whatever is there on the left hand side of salt bridge, that is anode. Zinc is losing 2 electrons and becoming zinc 2 plus. Whatever be the cell, it is always anodic oxidation and cathodic reduction. Here tin X plus is gaining X number of electrons and becoming tin, so that is reduction. So therefore E cell standard is equal to cathode value is 0.008 minus anode value, the reduction potential is given as minus 0.763. So therefore this is equal to 0.771 volt. Therefore 0.801 is equal to 0.771 minus 0.06 divided by n log 10 to the power minus 2. We can bring this 10 to the power minus 2 here. We have another minus sign here. So therefore that would become plus. Therefore 0.801 minus 0.771 is equal to 0.12 divided by n. Therefore this would be 0.030, and that is equal to 0.12 by n. Therefore n is equal to 12 times 10 to the power minus 2 divided by 30 times 10 to the power minus 3. We will have 10 to the power minus 1 in the denominator, 1010 we can cancel. So therefore n value is equal to 4. Therefore 4 electrons are involved. Therefore the correct answer here is 4. Consider the following half cell reaction. Dichromate ion gaining 6 moles of electrons and becoming chromium 3 plus, 2 moles of chromium 3 plus. The reaction was conducted with a ratio of concentration of chromium 3 plus whole square, because we have the stoichiometric coefficient 2, divided by dichromate ion, and that is equal to 10 to the power minus 6. Basically, part of the reaction quotient value is given. In that case, what is the pH value at which the EMF of the half cell will become 0? We have to find out the nearest integer. Half cell reduction potential is given, and this is the term that we use in the Nernst equation. Now, the condition given here is EMF of the half cell will become 0. So, that means the E cell value is equal to 0 volt. That is the condition given here. Therefore, we know that as per Nernst equation, E cell is equal to E cell standard minus 2.303 times RT by NF log Q. Q is the reaction quotient. So, in this case, the quotient is equal to concentration of chromium 3 plus whole square, and we don't enter liquids or solids in the reaction quotient. So, therefore, we can leave the products as it is, divided by concentration of dichromate ion times concentration of H plus to the whole power 14, because we have 14 as the stoichiometric coefficient. Therefore, let us substitute this in the Nernst equation. Now, before doing that, we also know that E cell standard is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. One question that may come to many of you is, what is the reduction potential of the anode here? That value is not given. The reaction provided is a half cell reaction and not a full electrochemical cell. However, if you carefully see the standard half cell reduction potential in this case, they have mentioned H plus. What this means is that the potential of this single electrode measured against a standard hydrogen electrode. We know that for standard hydrogen electrode, it is 0 volt because that is a reference electrode. So, that is a tricky part in this question. So, therefore, for the anode, we have to take it as 0. Please do not think that the value is not given. So, therefore, for the cathode, the value given is 1.33 volt. So, therefore, the E cell standard is equal to 1.33 volt. Therefore, 0 is equal to 1.33 minus 0.059 divided by 6, because 6 moles of electrons were involved in the reduction process, times log 10 to the power minus 6. Why 10 to the power minus 6? Because the concentration of chromium 3 plus whole square divided by concentration of dichromate ion is given as 10 to the power minus 6 times we have H plus ion concentration. So, if we bring that up, then that is H plus concentration to the whole power minus 14, because we have 1 by H plus to the power plus 14. So, we brought it up, therefore, it became minus. Now, this is log A times B. Log A times B is log A plus log B. So, let us rearrange this equation. 0.059 divided by 6 times minus 6. We are just bringing this minus 6 to the front. Log 10 base 10 is 1. So, times 1. And then let us bring this minus 14 also to the front. So, therefore, minus 14 times log H plus ion concentration. And we know that pH is equal to negative logarithm of H plus ion concentration. So, therefore, let us substitute that here, and this is equal to 1.33. Therefore, 0.059 divided by 6 times minus 6 plus 14 times pH is equal to 1.33. So, therefore, minus 6 plus 14 times pH is equal to 1.33 times 6 divided by 0.059. 1.33 times 6 would be 6 times 3, 18, remaining 1. 6 times 3 again, 18 plus 1, 19, remaining 1, 6 times 1, 6 plus 1, 7. So 7.98 divided by 0.059, and that we can write it as 798 times 10 to the power minus 2 divided by 59 times 10 to the power minus 3. So we will have 10 to the power minus 1 in the denominator. So if we send that up, then it would be 7980 divided by 59. This is what we need to figure out now on the right hand side. So let's do the long division. 7980 divided by 59. We can do it one time. So 59 remaining 20. Let's bring down the 8. Now we can do it 3 times. 3 times 59 is 177, remaining 31. Let's bring down this 0 also. So now we can do it 5 times. 5 times 59 is 295, remaining 15. We can't divide, so put a 0 and raise it to the decimal. So now we can do it 2 times. 2 times 59, 118, remaining 32. We can't divide, so put a 0. Now we can once again do it 5 times. So therefore 135.25. So minus 6 plus 14 times pH is equal to 135.25. So therefore pH is equal to, let's bring the minus 6 to the other side. In that case it would be 141.25 divided by 14. So therefore this will be approximately equal to 10. So therefore the correct answer in this case is pH is equal to 10. 10 is the correct answer here. The cell potential for the given cell at 298 K is given as 0.31 volt. The pH of the acidic solution is found to be 3, whereas the concentration of Cu2 plus is 10 to the power minus x molar. What is the value of x is? Standard reduction potential of copper 2 plus becoming copper is given, and also this is the term that we use in the Nernst equation, that is also given. We know that Nernst equation is E cell is equal to E cell standard minus 2.303 RT by NF log Q, where Q is the reaction quotient. Here, what is the anode and what is the cathode? We have a salt bridge here. So whatever is there on the left hand side of salt bridge, that is the anode, isn't it? And whatever is there on the right hand side of salt bridge, that is the cathode. Anode, oxidation happens. So therefore H2 gas giving 2H plus and releasing 2 electrons. So this is happening at the anode, anodic oxidation, cathodic reduction. And then at the cathode, reduction happens, copper 2 plus gains 2 electrons, becoming copper solid. Therefore the net reaction is H2 gas plus Cu2 plus giving 2H plus copper solid. This is the net reaction. Therefore quotient here is concentration of H plus whole square, because we have the stoichiometric coefficient 2 here, and we don't enter solids in the reaction quotient equation because that is constant, divided by concentration of H2, that we can take it as 1 bar, partial pressure of H2. So therefore simply multiplying 1 with the concentration of copper 2 plus. So that's our reaction quotient. And we also know that E cell standard is equal to the standard value for the cathode minus the standard value for the anode. So here H2 is the reference electrode. So for the reference electrode, we keep it as 0 volt. That is not given, but this is something you are supposed to know it. And the platinum acts as an inert conductive metal substrate that facilitates the redox reaction between H2 and H plus in the standard hydrogen electrode. So therefore this value is 0.0 volt, and for the cathode the value is given as 0.34 volt. So therefore the E cell standard value is 0.34 volt. So let's plug in this in the next equation, and the E cell value is given as 0.31 volt. E cell standard value that we got is 0.34 volt minus 0.06 divided by 2, because there were 2 moles of electrons, isn't it, as per the redox equation, times log concentration of H plus was given as 10 to the power minus 3. Why? Because pH value was given as 3. We know that pH is equal to negative logarithm of H plus ion concentration. So therefore H plus ion concentration must be equal to 10 to the power minus 3, so that we can get the pH value as 3. So therefore 10 to the power minus 3 whole square divided by concentration of copper 2 plus, and this will become 0.03. Now for the concentration of copper 2 plus, let's write the value as 10 to the power minus x, because that is what given in the question paper. So therefore 0.31 is equal to 0.34 minus 0.03 times log 10 to the power minus 6 divided by 10 to the power minus x. So if we bring this one up, it would become positive. So therefore it would be log 10 to the power x minus 6, isn't it? So this x minus 6 we can bring it to the front. Therefore 0.31 is equal to 0.34 minus 0.03 times x minus 6, log 10 base 10 is 1. So therefore 0.03 times x minus 6 is equal to 0.34 minus 0.31. I just brought this term to the other side. So therefore x minus 6 is equal to 0.03 divided by 0.03. So therefore x minus 6 is equal to 1. Therefore x is equal to 7. Therefore 7 is the correct answer here. So therefore the value of x here is 7. That's the correct answer. Here is a conceptually intensive question from electrochemistry. This question is not difficult to solve, but concept clarity is required to solve a question like this. In a cell, the following reactions takes place. The standard electrode potential for the spontaneous reaction in the cell is x times 10 to the power minus 2 volt at 298 K. What is the value of x is? Now, if Fe2 plus becoming Fe3 plus, what does it mean? That means oxidation, isn't it? Increase in oxidation number is oxidation, and decrease in oxidation number is reduction. I minus becoming I2. From negative it is becoming 0. Therefore, that is oxidation, or the other way to remember is losing electrons is oxidations, gaining electrons is reduction, and the reverse one is reduction. Now the question says spontaneous reaction. When a reaction would be spontaneous? Only when the standard Gibbs energy is negative, that is less than 0, then only it can be spontaneous. And we know that delta G standard is equal to minus NF E cell standard. So this means the E cell standard value that we are going to calculate here has to be positive. The question already gave a clue to us, isn't it? Because so that the delta G standard would be negative. Only if this value is positive, the E cell standard value is positive, then only the delta G standard would be negative, so that the reaction would be spontaneous. Now let us check whether they have given reduction potentials or not. Fe3 plus gaining an electron and becoming Fe2 plus, that is reduction. Therefore, this is a reduction potential. I2 gaining 2 electrons and becoming I minus or 2I minus. That is reduction, isn't it? So, therefore, reduction potentials are given here. If standard reduction potentials are given, then how to identify the species, like which one is the cathode, which one is the anode? The higher positive value should be the cathode. That is where the reduction will happen. So, therefore, this is the cathode and this is the anode, isn't it? Now, we know that E cell standard is equal to E cell standard of the cathode minus E cell standard of the anode. Both are reduction potentials. Sometimes people use this equation also, where E cell standard is equal to E cell standard of the anode oxidation plus E cell standard of the cathode reduction. Now, I prefer to use this equation because using this equation means that you have to change the sign. So, therefore, I don't want to do it. If you are comfortable changing sign and doing correctly, that's up to you. But keep it in mind that it's safe to use the first equation, because in that case we don't have to change the sign. So, therefore, the net reaction that is happening here is Fe3 plus gains an electron becoming Fe2 plus, that is reduction, because whatever be the cell, it is always anodic oxidation and cathodic reduction. And then 2I minus, that is iodide becoming iodine, that is oxidation. Now, to balance the equation, we have to multiply this entire equation by 2. Therefore, the net reaction is 2Fe3 plus 2I minus giving 2Fe2 plus I2. Now, keep it in mind that standard electrode potentials are intensive properties. They are not extensive properties. Standard electrode potentials are intensive properties. That means they depend on the nature of the substance and not the amount. Therefore, just because we multiplied here by 2, it doesn't mean that we have to multiply the standard reduction potential by 2. We shouldn't do that. Therefore, E cell standard is equal to cathode, that is 0.77, E cell standard of the cathode minus E cell standard of the anode, that is 0.54. Therefore, that is equal to 0.23, which we can write it as 23 times 10 to the power minus 2 volt. Therefore, 23 is the correct answer here. Nearest integer is 23. Given the equilibrium constant Kc of the reaction is 10 times 10 to the power 15, calculate the E cell standard of this reaction at 298 K. The term that we use in the Nernst equation at 298 K is given as 0.059 volt. We know that Nernst equation is E cell is equal to E cell standard minus 2.303 RT by NF log Q. Q is the reaction quotient. We also know that at the equilibrium, Kc is equal to Q. Also, at the equilibrium, delta G is equal to 0. This means E cell is equal to 0, isn't it? Because there is no net electron flow. Therefore, the cell potential is 0. This means E cell standard is equal to 2.303 RT by NF log Q. Here copper is becoming copper 2 plus, that means oxidation. Ag plus is becoming Ag, that means reduction. Therefore, at the anode, because whatever be the cell, it is always anodic oxidation and cathodic reduction. At the anode, copper solid is losing 2 electrons and becoming copper 2 plus. At the cathode, reduction is happening. Ag plus gains an electron and becoming Ag solid. But to balance the equation, we have to multiply this entire equation by 2. So therefore, the net reaction is copper solid plus 2Ag plus giving copper 2 plus 2Ag. Therefore, the quotient here is concentration of copper 2 plus divided by concentration of Ag plus whole square, because we have the stoichiometric coefficient 2 here. We don't write solids in the reaction quotient equation because they are constant. Now, this term is given as 10 to the power 16. Therefore, E cell standard is equal to 0.059 divided by 2, because 2 moles of electrons, times log 10 to the power 16. So therefore, 16 we can bring it here. This means 0.059 divided by 2 times 16, because log 10 base 10 is 1. So therefore, this is 8 times. This means 0.059 times 8. 59 times 8 would be 8 times 9, 72, remaining 7. 8 times 5, 40, so 47. So therefore, this will be 0.472 volts. The E cell standard value is. This means option 3 is correct. The closest value that we can see is this one. So therefore, option 3 is correct. For a cell involving copper and silver electrodes, the cell potential is found to be 0.43 volt at 298 K. What is the magnitude of standard electrode potential for copper 2 plus becoming copper is? We have to find out the answer in terms of 10 to the power minus 2 volt. Standard reduction potential of silver plus becoming silver is given as 0.80 volt, and this is the term we use in the next equation. We know that E cell standard is equal to standard reduction potential for the cathode minus standard reduction potential for the anode. So first we need to find out this term, and then we can figure out the final answer, because here they are asking the standard electrode potential for copper 2 plus becoming copper. So this is the standard reduction potential they are asking, and the cell potential value is given. Now at the anode, what will happen? At the anode, oxidation happens. Whatever be the cell, it is always anodic oxidation and cathodic reduction. This is the salt bridge. Therefore, on the left hand side we have the anode, on the right hand side we have the cathode. So this means at the anode, copper is losing 2 electrons and becoming copper 2 plus, whereas at the cathode, reduction is going to happen. So this means Ag plus is gaining an electron and becoming Ag solid, but we have 2 electrons involved at the anode. So therefore, we have to multiply this equation by 2 so that we can balance the equation. So this means the net reaction is copper solid plus 2 Ag plus is giving copper 2 plus 2 Ag solid. So that's the net reaction. So this means the reaction quotient is concentration of copper 2 plus divided by concentration of Ag plus whole square, because we have the stoichiometric coefficient 2 here. Now let us use the next equation. Next equation is E cell is equal to E cell standard minus 2.303 RT divided by NF log Q. So here E cell value is given, that is 0.43 volt. E cell standard we need to figure out, minus this term is given as 0.06. So therefore 0.06 volt divided by number of electrons involved is 2, and then log Q, that is concentration of Cu2 plus, that is 0.001 molar divided by 0.01 molar whole square, isn't it? So this one we can write it as 1 times 10 to the power minus 3. This one we can write it as 1 times 10 to the power minus 2. But we have square term here. So therefore this becomes 10 to the power minus 4. So this means eventually it becomes log 10 base 10. Log 10 base 10 is 1. So this means E cell standard is equal to 0.43 volt plus 0.03 volt, and that is equal to 0.46 volt. This is the E cell standard value. So this means we know that E cell standard is equal to standard reduction potential at the cathode minus standard reduction potential at the anode. So therefore this is equal to Ag plus becoming Ag minus Cu2 plus becoming Cu, and E cell standard is 0.46 volt, and this value is given as 0.80 volt. So therefore 0.46 volt is equal to 0.80 volt minus this one. So therefore copper 2 plus becoming copper, the standard reduction potential is equal to 0.80 minus 0.46, and that is equal to 0.34. But we need the answer in terms of 10 to the power minus 2. So therefore 34 times 10 to the power minus 2 volt. So this means 34 is the correct answer. So therefore 34 times 10 to the power minus 2 volts. What is the number of electrons in 0.2 times 10 to the power minus 5 Faraday is? We know that charge of 1 mole of electrons is equal to 1 Faraday. 1 mole of electrons means Avogadro number of electrons, that is 6.022 times 10 to the power 23 electrons is equal to 1 Faraday. Now here they are asking 0.2 times 10 to the power minus 5 Faraday, how many electrons will be there? So therefore we just need to cross multiply. So therefore x is equal to 0.2 times 10 to the power minus 5 Faraday times 6.022 times 10 to the power 23 electron. So therefore let's write this as 2. In that case this will become 10 to the power minus 6. Here we have 10 to the power 23. Together this will become 10 to the power 17. 2 times 6.022, that would be 12.044 times 10 to the power 17 electron. Is that given in the option? No. So this is definitely wrong. How about if we multiply and divide by 10? In that case we can write this as 1.2044 times 10 to the power 18 electron. That is given in option 4. So therefore option 4 is correct. For the cell, the correct next equation is which one? Next equation is the one that relates cell potential with the concentration of the species involved in an electrochemical reaction. Now, we know that E cell is equal to E cell standard minus RT by NF ln and then the reaction quotient. So, let us say if you have a reaction this way, X times A plus Y times B giving, let us say, M times C plus N times D, then you can write the reaction quotient this way: concentration of C to the power of M times concentration of D to the power of N divided by concentration of A to the power X times concentration of B to the power Y. Now, for a cell, this double vertical bar, what it means is that it means salt bridge. So, it is always salt bridge in the middle, and then on the left hand side it is the anode half cell, and then on the right hand side it is the cathode half cell. The single bar represents phase boundary. This is phase boundary, which means that this silver here is solid. Likewise, here too the magnesium here is solid. It is not given, but the phase boundary basically tells us that it is not in aqueous medium, it is solid. We know that whatever be the cell, it is always anodic oxidation and cathodic reduction. Therefore, the half cell reaction that is happening at the anode is magnesium losing 2 electrons and giving Mg2 plus, and the half cell reaction happening at the cathode is Ag plus gaining an electron and becoming Ag solid. Now, 2 electrons are involved on the anode side. That means we need to multiply this entire half cell reaction with 2. So, now we can balance this and write the balanced equation. So, therefore, the net is Mg solid plus 2Ag plus giving Mg2 plus, that is in the aqueous medium. This is also aqueous medium, plus 2Ag solid, and we don't write the solid in the reaction quotient. So, therefore, the reaction quotient here is Mg2 plus divided by Ag plus square with a negative sign. Do we see anything like that in the option? No. In 1 we don't see it. In 2 we see it, but the reaction is reversed. So, therefore, that should be the correct option, because in 3 it is Mg2 plus written, but then Ag plus is not squared, therefore, that is wrong. And in 4 it is written in the reverse way, therefore, this is also wrong. So, the only correct option is option 2. In the above diagram, the standard electrode potentials are given in volts over the arrow. What is the value of E cell standard for FeO4 2 minus becoming Fe2 plus? First of all, we need to figure out the oxidation state of Fe in the ferrite ion. We don't know that, therefore, let us keep it as X plus 4 times. We put minus 2 for oxygen typically, therefore, 4 times minus 2, that is equal to minus 2, because the net charge given here is 2 minus. Therefore, X minus 8 equal to minus 2, therefore, X is equal to plus 6. Therefore, the oxidation state of Fe in FeO4 2 minus 6 plus 6. This means this is undergoing reduction, isn't it? This process requires how many moles of electrons? We require 4 moles of electrons. So, here it is plus 6. If plus 6 is becoming plus 3, that requires how many moles of electrons? That requires 3 moles of electrons. If Fe3 plus becoming Fe2 plus, that requires how many moles of electrons? That requires 1 mole of electron. If Fe2 plus is becoming Fe, then that requires 2 moles of electrons, because everywhere it is reduction, isn't it? If plus 6 has to become plus 3, then it has to gain 3 electrons, isn't it? If FeO4 2 minus gains 3 electrons, then only it can become Fe3 plus. But the question here is, when FeO4 2 minus becomes Fe2 plus, what is the E cell standard value? We can calculate that. We know that delta G standard is equal to minus NF E cell standard, where N is the number of moles of electrons, F is the Faraday constant, and E cell standard is the reduction potential. So, therefore, we can write it this way, minus N4F E4 cell that we need to calculate is equal to minus N1F E1 cell minus N2F E2 cell. By the way, we do not need to involve delta G3 standard here, because the question is asking plus 6 to plus 2 oxidation state, what is the E cell value? Therefore, we do not need to involve this process. Therefore, N4 value is 4, because it requires 4 moles of electrons, times F times E4 standard is equal to minus 3 times F times E1 standard value is given as 2 volts. Therefore, times 2 minus N2 value is 1 times F. E2 standard value is given as 0.8 volts. Therefore, times 0.8. Therefore, minus 4 E4 standard is equal to, F is constant everywhere, therefore, we can remove that. This is equal to minus 6, because 3 times 2 minus 0.8. Therefore, E4 standard is equal to, because minus is common on both sides, this is minus 6.8 minus E4 standard. Minus is common on both sides, therefore, I am removing the minus. So, E4 standard is equal to 6.8 divided by 4. So, therefore, that is equal to, this is 1 times and then 2 remaining 28, 7 times 4 is 28, therefore, 1.7. Therefore, E4 standard is equal to 1.7 volt. So, this means option 1 is correct. If the standard electromotive force of a cell for a given reaction has a negative value, which of the following gives the correct relationships for the values of delta G naught and K equilibrium? We know that delta G naught is equal to minus NF E cell standard, where N is the number of moles of electrons transferred in the redox reaction, F is the Faraday constant. So, if E cell standard is negative, then what would happen to delta G standard? Delta G standard would become positive, and therefore, it is greater than 0, because if this is a negative number, we have another negative sign here. So, negative negative would become positive. So, this means option 1 is wrong and option 2 is also wrong. We also know that delta G standard is equal to minus 2.303 times RT times log K equilibrium base 10. We know that log value of any number between 0 to 1 is negative, isn't it? So that the overall value can become positive. So, this means K equilibrium has to be greater than 0 but less than 1, so that we can get a negative number, and that negative number multiplied with this negative number would become positive, so that delta G would be greater than 0. So, this means K equilibrium has to be less than 1. So, therefore, option 3 is the correct choice here, because if K equilibrium is greater than 1, then delta G will become negative, isn't it? If K equilibrium is greater than 1, then delta G won't become positive, it would become negative. That's why option 4 is wrong. Hello everyone, here is a question from electrochemistry. The standard electrode potentials for a few half cells are mentioned below. Which one of the following cells gives the most negative value for delta G naught? We know that delta G naught is equal to minus NF E cell standard, where N is the number of moles of electrons, and F is the Faraday constant, which is 96,500 coulomb per mole, and E standard of the cell is equal to E standard of the cathode, that is the reduction potential, minus E standard of the anode, that is also reduction potential. Now, some instructors do write it this way, that is E naught standard of the anode oxidation plus E naught standard of the cathode reduction. Both are okay, but when you use this formula, you need to constantly change the sign, because normally the reduction potentials will be given in the question paper. Now, let us just verify whether they are reduction potentials or not. Cu2 plus is becoming Cu. When Cu2 plus will become Cu? If it gains 2 electrons, then it can become Cu. That means reduction. Likewise, if you see, whatever the values given here, they are all reduction potentials, isn't it? So, when we use oxidation potentials, we have to change the sign of the reduction potential, which I don't want to do it. Therefore, I prefer to use this formula. If you are using this formula, make sure that you are changing the sign appropriately. Otherwise, you will get the wrong answer. Now, when delta G will be negative? Delta G will be negative if E naught of the cell is positive, isn't it? That's the only way delta G can be negative. Basically, the delta G negative is going to be decided by this single value, because N is constant here. How N is constant? The number of moles of electrons is going to be 2 moles everywhere. Now you might be thinking that here we have only like 1 mole, here we are having 2 mole. But the thing is, if you write the net reaction, so for example, for this cell, if we are writing the net reaction, at the anode oxidation happens. No matter what the cell, it is always anodic oxidation and cathodic reduction. So zinc losing 2 electrons and becoming zinc 2 plus. At the cathode, reduction happens. So therefore, Ag plus gaining an electron and becoming Ag. But to balance the reaction, we have to multiply this entire equation with 2, isn't it? Otherwise, we can't balance the equation. So therefore, everywhere the number of moles of electrons is going to be 2. So therefore, that is also constant. So the net reaction in this case is zinc plus 2Ag plus giving zinc 2 plus 2Ag. That's the net reaction. So therefore, N is constant everywhere, F is constant. So we just have to determine E cell standard. If that has a more positive value, then that is our correct answer. So let's determine the values one by one. And before doing that, let's talk briefly about the cell notation. There is a phase change here. So this is the phase boundary. So basically it means that these are all solids and these are all in the aqueous medium. And this double vertical bars indicate that there is a salt bridge here to maintain the neutrality of the solution. That completes the circuit. So once again, these are all in the aqueous medium and these are all in the solid phase. So now E naught of the cell in the first case is equal to cathode minus anode, both reduction potentials. That's the way we are going to calculate. So this is all cathode, this is all anode. E naught of the cell is E naught of the cathode reduction potential, that is Ag plus becoming Ag, so 0.80 volt, minus reduction potential at the anode, so that is minus 0.76 volt. So therefore together it is 1.5 0.56 volt because negative negative will become positive. And then number 2 E cell standard in this case is reduction potential of the cathode, that is Mg2 plus becoming Mg, so minus 2.37 volt minus reduction potential of the anode, that is minus 0.76 volt. So therefore this will be equal to minus 1.61 volt. So therefore this is definitely not the correct answer, because in the delta G equation there is another negative sign. So with this negative sign it will become positive. So it is non-spontaneous. And then number 3 E cell standard is equal to cathode minus anode. So once again minus 2.37 volt minus and then 0.80 volt. Therefore this will be equal to minus 3.17 volt. And then for number 4 it would be E cell standard equal to cathode minus anode. So cathode 0.80 volt minus anode 0.34 volt. So therefore this will be positive 0.46 volt. So here we have positive 1.56 volt, and then we will be multiplying with the 2 and then the Faraday constant. So therefore this will be most negative. Therefore option 1 is the correct choice here. We are given with the following cell reaction. H plus ions are gaining 2 electrons and getting reduced to H2. If E cell for the reaction is given by minus x times 10 to the power minus 3 volt, find out the value of x. We have to find out the nearest integer. Partial pressure of H2 is given as 2 atm. H plus ion concentration is given as 1 molar, and this is the term that we use in the Nernst equation. We know that we can use the Nernst equation to calculate the EMF of a cell, whether it is a full reaction or a half cell reaction. Therefore E cell is equal to E cell naught minus 2.303 RT by NF log Q. Here the half reaction that happens at the cathode in the standard hydrogen electrode is given. Basically H plus is gaining 2 electrons and getting reduced to H2. So therefore E cell for the standard hydrogen electrode is equal to 0 volt. This is something expected to know because this is our reference. It is not given in the question, but we know that E naught of the cell for the standard hydrogen electrode is 0 volt because that is our reference point. Therefore E cell is equal to 0 minus n value here is 2 because it involves 2 electrons. Therefore minus 1 by 2 times 0.06 volt times log partial pressure of H2 divided by H plus square. Therefore E cell is equal to minus 1 by 2 times 0.06 volt times log 2 by 1 square, and that will be simply log 2. Therefore this is equal to, this will become 0.03, which I am writing it as 3 times 10 to the power minus 2 volt times log 2 value is 0.3010, which I am taking it as 3 times 10 to the power minus 1 approximately. So therefore this will be equal to minus 3 times 3 is 9 minus 9 times 10 to the power minus 3. Therefore the value of x is 9. That is the correct answer here. Here is a question based on electroplating. 1 Faraday electricity was passed through Cu2 plus Cu, where the concentration of Cu2 plus is 1.5 molar, and 0.1 Faraday electricity was passed through Ag plus Ag, where the concentration of Ag plus is 0.2 molar electrolytic cells. After these two cells were connected, as shown below, to make an electrochemical cell, What is the EMF of the cell thus formed at 298 K? We have to find out the answer in terms of millivolts. The given values are reduction potential of Cu2 plus to Cu and the reduction potential of Ag plus to Ag, and in the next equation whatever the term we use, that was given as 0.06 volt. So we have to use Nernst equation to find out the electromotive force. Nernst equation is E cell equal to E cell standard minus 2.303 RT divided by NF log Q base 10. Now E cell standard is the standard reduction potential of the cathode minus the standard reduction potential of the anode. This problem has two layers. First, we need to figure out the new concentrations, because concentration of Cu2 plus and concentration of Ag plus is given, but they are initial concentrations. Once the electricity is being passed, the concentration of Cu2 plus as well as the concentration of Ag plus is going to change. So that we need to figure out first before we apply those terms to the Nernst equation. So let us first find out the new concentrations. We have Cu2 plus on one side. Cu2 plus, if it gains 2 electrons, then it can become Cu. So that means to convert it into Cu, we require 2 mole of electrons. We know that 1 mole of electrons, the charge of 1 mole of electrons is equal to 1 Faraday, that is equal to 96,500 coulomb per mole. But do we have 2 Faraday here? No, we have only 1 Faraday electricity. So therefore, how much it would get converted? Only half a mole, isn't it? If we have 2 Faraday electricity, then we can get 1 mole of copper. But we have only 1 Faraday of electricity. So therefore, with that, we can get only half a mole of Cu, isn't it? So therefore, now what the concentration of Cu2 plus would be? The new concentration. Initially, the concentration of Cu2 plus is 1.5 molar before the electricity is passed. So after the electricity is passed, what it would become? So Cu2 plus left is equal to whatever is the initial value, Cu2 plus initial minus Cu2 plus consumed, isn't it? So now how much is consumed here? 0.5 molar is consumed. So 1.5 molar minus 0.5 molar, therefore that is equal to 1 molar. So that's the new concentration of Cu2 plus. Likewise, we have Ag plus. If Ag plus gains 1 electron, then it would become Ag. But for that 1 Faraday is required. But how much we are passing? Only 0.1 Faraday. That's what is given in the problem, isn't it? So if we are passing only 0.1 Faraday, we will get 0.1 Ag. So therefore, the concentration of Ag plus left is equal to whatever the concentration we have for Ag plus initially minus Ag plus consumed, isn't it? So therefore, this will be equal to, initially we have 0.2 molar minus consumed is 0.1 molar. So therefore, the new concentration is 0.1 molar. This is the value we should use in the Nernst equation. If we use the older values, you cannot get the correct answer. Now let's come to the actual problem. We figured out that what are the new concentrations of Cu2 plus as well as Ag plus. Now we need to figure out where the oxidation is happening and where the reduction is happening. The reduction potentials are given. We know that if the reduction potential is higher for a given species, What it means? It means it can easily get reduced. That means it is a strong oxidizing agent. Here 0.34 is definitely less than 0.80. So a higher and more positive reduction potential indicates that it has a greater tendency for a species to gain electrons and get reduced easily. So higher standard reduction potential means it has the oxidizing tendency. It is a measure of the oxidizing tendency, isn't it? So therefore, which one will get reduced here quickly? Ag plus will get reduced quickly because that has the higher value. So therefore, this is the cathode and this is the anode here. The simple way that you can remember is whichever has the higher reduction potential, that will get reduced quickly. That has the tendency to gain the electron quickly and becomes a neutral species. Okay. So therefore, in this case, reduction is happening at this end because it is always anodic oxidation and cathodic reduction. So reduction is happening here. Ag plus gaining an electron and becoming Ag, and here oxidation is happening in the anode. So Cu becoming Cu2 plus and giving 2 electron. So that means the electron flow is this way, isn't it? So that part is clear. Now let's come to the Q part. So we mentioned that at the anode oxidation is happening. So therefore this is Cu giving Cu2 plus 2 electrons, and then at the cathode reduction is happening. Ag plus gains an electron and becomes Ag. To balance the equation, we have to multiply by 2 here. So this is 2, this is 2, and this is also 2. Therefore 2 electron we can cancel. Therefore 2 Ag plus Cu giving Cu2 plus 2 Ag. Therefore the quotient here is product here Cu2 plus concentration divided by reactant Ag plus square, because we have the stoichiometric coefficient 2 here. We don't write the solids in the reaction quotient equation. So therefore E cell is equal to E standard cathode minus E standard anode minus 1 by n times this 2.03 RT by F is given as 0.06 volt times log concentration of Cu2 plus that we found is 1 molar, isn't it? This is Cu2 plus divided by Ag plus square. So therefore the concentration of Cu2 plus, that is the new concentration that we found, was 1 molar divided by concentration of Ag plus, that is the new concentration of Ag plus that we found was 0.1. So this is 1 divided by 0.1 square. 0.1 we can write it as 1 by 10 whole square. So therefore this is 1 by 100. So that we can put it as simply, when it comes up it would become 100. I am writing it as 10 square. So therefore this will be equal to E standard cathode is 0.80 volt minus E standard anode is 0.34 volt minus n factor is 2 times 0.06 volt times this will be 2 log 10 base 10. So this 2 we can cancel. So therefore this will be 0.46 volt minus 0.06 volt, and that is equal to 0.40 volt. But we need the final answer in terms of millivolts. So therefore this will be 400 millivolt. The EMF of the cell will be 400 millivolt. So therefore 400 is the correct answer here. Hello everyone, here is a question based on Colehouse law. if the molar conductivity of a 0.050 molar solution of a monobasic weak acid is 90 Siemens centimeter square per mole, what is its extent of degree of dissociation will be? We know that as per Colehouse law, at infinite dilution, the limiting molar conductivity of an electrolyte is equal to the sum of the limiting molar conductivities of its constituent ions. Therefore, here it is mentioned as monobasic weak acid, that means it is univalent. Therefore, we can sum up these two, lambda 0 of cation and lambda 0 of anion. Therefore, that is equal to 349.6 plus 50.4. Therefore, this will be equal to 400 Siemens centimeter square per mole. Now, the degree of dissociation for a weak electrolyte alpha is equal to molar conductivity at a particular concentration. Here it is given as 0.050 molar divided by limiting molar conductivity, that is at infinite dilution. So, therefore, this will be equal to 90 Siemens centimeter square per mole divided by 400 Siemens centimeter square per mole. 1010 we can cancel. So, we have to divide 9 by 40. We can't divide, so put a 0. So, 2 times will be 80, remaining 10. We can't divide, so put a 0 once again. 2 times will be 80 once again, remaining 20. We can't divide, put a 0. 5 times 40 will be 200. So, therefore, this will be 0.225. So, this means option 3 is correct. 2 ampere current is allowed to pass through molten AlCl3 for 30 minutes. Find the mass in milligrams of aluminum deposited at cathode. We need to find out the nearest integer. Here AlCl3 is undergoing electrolysis. This means that in the aqueous medium we will be having Al3 plus. Therefore, the half reaction happening at the cathode is reduction. Al3 plus gains 3 electrons and we will be getting Al solid. Cathode reduction. What this means is that if we have 1 mole of Al3 plus, we require 3 moles of electrons so that we can get 1 mole of aluminum. That is the stoichiometry here. Now, we need to calculate the mass of Al deposited at the cathode in milligrams. As per Faraday's first law of electrolysis, mass of the substance deposited or liberated at any electrode is directly proportional to the quantity of electricity or charge Q passed. Q is equal to current times time. Therefore, mass is proportional to current times time. To get rid of the proportionality factor, we introduce a constant called Z, that is the electrochemical equivalence. Therefore, mass is equal to Z times current times time. Now, Z is equal to equivalent mass divided by valency factor. Valency factor in this case is found as 3 and equivalent mass is equal to molar mass divided by Faraday constant. Therefore, mass is equal to molar mass times current times time divided by valency factor times Faraday constant. Therefore, this is equal to molar mass of aluminum is 27 gram per mole, current is 2 ampere, time is 30 minutes, but we need to convert it into seconds. Therefore, multiply by 60 divided by 3 times 96,500 coulomb per mole. Ampere second is coulomb. Therefore, coulomb we can cancel, per mole also we can cancel, 20 we can cancel here. So, this is 3 times, this is 9 times 3 is 27, therefore, this is 9. So, 9 times 2 18, 3 times 6 18, therefore, 18 times 18 is 324 divided by 965. That is what we need to find out, but the answer is going to be in grams. which we need to convert into milligrams. Therefore, 324 divided by 965, we can't divide it, so put as 0. 3 times will be 2895 and the remaining will be 5 here, 13 minus 9, that will be 4, and then 11 minus 8, 3. Once again we can't divide it, so put as 0. Again 3 times, so 2895 again, 5 here, 14 minus 9, therefore 5, 13 minus 8, 5. We can't divide once again, therefore put as 0. And then 5 times will be 4825, and then 5 here, 4 minus 2, 2, and then 15 minus 8, 7. Once again we can't divide, so put as 0. 7 times will be 6755. So therefore, now we can write that mass is equal to 335.7 times 10 to the power minus 3 gram, which we can write it as 336 milligram. The aluminum deposited at the cathode is 336 milligrams. That's the correct answer. M is equal to 336 milligrams. Here is a question from electrochemistry. An electrolytic cell consists of 2 copper electrodes immersed in a solution of copper 2 sulfate. What is the result of passing 0.35 ampere current through this cell for 1300 seconds? Let us assume that we have a beaker containing copper sulfate solution in the aqueous medium. We have 2 copper electrodes. Let's say one is the anode and then another copper electrode is the cathode. Electron flows towards cathode. Both of them are copper. So electroplating is what happens in this. This means that whatever the mass lost by the anode is gained by the cathode. So we just need to figure out the mass here. Therefore, as per Faraday's first law of electrolysis, mass is proportional to the quantity of electricity or charge Q passed. Therefore, M is proportional to Q. Q equal to current times time. Therefore, M is proportional to current times time. To get rid of the proportionality constant, we introduce a constant called Z, that is the electrochemical equivalence. Therefore, the half reaction happening at the cathode in this case is we will be having copper 2 plus in the aqueous medium, that will gain 2 electrons and will become copper solid. So this will be happening at the cathode reduction. Therefore, the valency factor here is 2, because when we have 1 mole of copper 2 plus, we require 2 mole of electrons so that we can get 1 mole of copper solid. That's the stoichiometry here. Z is equal to equivalent mass divided by valency factor. Valency factor in this case is 2 and equivalent mass is equal to molar mass divided by Faraday constant. Therefore, mass is equal to molar mass times current times time divided by valency factor times Faraday's constant. So let's figure out the mass. Therefore, mass is equal to molar mass of copper is approximately 64 gram per mole. Current is 0.35 ampere and the time is 1300 seconds divided by 2 times 96,500 coulomb per mole is the Faraday's constant. Ampere second is coulomb, therefore coulomb cancel, per mole also we can cancel. This we can put it as 32. Therefore, 32 times 13, that would be 416 times 0.35 divided by 965. Therefore, this will be 145.60 divided by 965. Let us take it approximately as 146. We can't divide it, so put as 0. One time will be 965, 10 minus 5, 5, 15 minus 6, 9, 13 minus 9, 4. We once again can't divide it, so put as 0 again. 5 times 965 will be 4825, remaining 125. So mass is approximately 0.15 gram. This means that the mass of the anode decreases by 0.15 gram because that amount is gained by the cathode. Therefore, option C is correct. For the cell reaction where iodide giving iodine, the E cell standard value is 0.24 volt at 298 Kelvin. What would be the standard Gibbs energy of the cell reaction? We know that delta G standard is equal to minus NF E cell standard. Here N value we need to figure it out. 1 Faraday is approximately 96,500 coulomb per mole. E cell value standard is given. We know that 1 joule is equal to 1 coulomb times 1 volt. Here the half reactions happening are as follows. At the cathode, the ferric ion gains an electron and becomes ferrous ion. This is reduction. At the anode, oxidation will be happening. Anodic oxidation, cathodic reduction. Two of the iodide ions loses 2 electrons and gives us the iodine molecule. To balance the entire cell reaction, we need to multiply the half reaction happening at the cathode by 2. That means our N value is 2 here. Delta G naught is equal to minus 2 times 96,500 coulomb per mole times 0.24 volt. Let us cut down these two zeros, make 0.24 as 24. Therefore, 24 times 2 is 48. Therefore, 48 times 965 coulomb volt is joules. Therefore, joules per mole. Let us write this as 1000. If we do that, then it is minus 48,000 joules per mole. If we write it in kilojoules per mole, then this value is minus 48 kilojoules per mole. Therefore, approximately we can take minus 46.32 kilojoules per mole as our final answer. Therefore, option 1 is correct. What would be the mass of copper deposited in grams by passing 9.6487 ampere current through a voltmeter containing copper sulfate solution for 100 seconds? Copper sulfate is undergoing electrolysis here, which means in the aqueous medium we will be having copper 2 plus. The reaction happening at the cathode, half reaction happening at the cathode, is copper 2 plus gains 2 electrons and we will be getting copper solid. So, this will be the half reaction happening at the cathode. So, if we have 1 mole of copper 2 plus in the aqueous medium, we require 2 moles of electrons so that we can get 1 mole of copper solid. That is the stoichiometry here. Now, we need to calculate the mass of copper deposited in grams. As per the Faraday's first law of electrolysis, the mass of the substance deposited or liberated at any electrode is directly proportional to the quantity of electricity or charge Q passed. We know that Q is equal to current times time. Therefore, mass is proportional to current times time. To get rid of the proportionality factor, we introduce a constant here called Z, that is the electrochemical equivalence, which is equal to equivalent mass divided by Faraday. Equivalent mass is equal to molar mass divided by valency factor. Valency factor here is identified as 2. Therefore, mass we can easily calculate. Mass is equal to molar mass times current times time divided by 2 times Faraday. That is the equation we are going to use. Therefore, mass is equal to 63 gram per mole times current is 9.6487 ampere, time is 100 seconds, ampere second is coulomb divided by 2 times 96487 coulomb per mole. This will cancel. This one we can write it as 96487 times 10 to the power minus 4. If we do that, then we can cancel this one also. This will be 10 to the power minus 2. Therefore, 0.63 grams divided by 2. Therefore, this will be 0.315 grams. That's the correct answer. Therefore, option 2 is correct. 4 different conversion reactions are given in list 1, which we need to match with the number of Faradays required in list 2. We know that 1 Faraday is equal to charge of 1 mole of electrons. The actual value is approximately 96,500 coulomb per mole. Here we don't have to worry about the actual value. We need to figure out how many moles of electrons are required for each conversion reaction. The first reaction given is 1 mole of H2O to O2. The stoichiometry here is not specified. 1 mole of H2O would actually give half a mole of O2 and 1 mole of H2. The stoichiometry is specifically mentioned for the water, and therefore we need to figure out for 1 mole of water what is the charge required. This is half a mole, this is 1 mole. If we have 2 moles of water, you would get 1 mole of O2 and 2 moles of H2. In presence of an acid, the half reactions happening are as follows. At the cathode, reduction will be happening. If you have 2 H plus ions, then we get H2 gas. At the anode, oxidation will be happening. So, if we have 1 mole of water, that would give half a mole of O2 and 2 H plus, and the charge required is 2 moles of electron. That means 2 Faraday. If we are calculating as 4 Faraday, keep it in mind that you are calculating that value for 2 moles of water. For 1 mole of water, the charge required is 2 moles of electrons, and therefore 2F is the correct choice here. In the next case, 1 mole of MnO4 minus to Mn2 plus. This is a reduction reaction. Permanganate ion is getting reduced to Mn2 plus. Keep it in mind that increase in oxidation number is oxidation, decrease in oxidation number is reduction. This is obviously a reduction reaction, because if we put minus 2 for each oxygen, then this will be minus 8 and this will be plus 7. So, plus 7 is becoming plus 2. That means this is a reduction reaction, and we need 5 moles of electrons. That means 5 Faraday. Therefore, B matches with 4. A matches with 2, B matches with 4. The only option where we see that result is option 1. Therefore, C should actually be 3 Faraday. Let us cross check that. This is another reduction reaction. If you have calcium 2 plus, gains 2 electrons and becomes calcium. So, we have 1 mole here, 2 mole here, 1 mole here. But the question is for 1.5 mole of calcium 2 plus. And therefore, 2 times 1.5, and that will be equal to 3. That means 3 Faraday. And then in option 4, ferrous oxide is becoming ferric oxide. That is an oxidation reaction, because here it is plus 2, here it is plus 3. That requires only 1 mole of electrons. Therefore, C matches with 1 and D matches with 3. Therefore, the correct choice is option 1 here. What is the time required to produce 0.10 mole of chlorine gas using a current of 3 amperes during the electrolysis of molten sodium chloride? Chlorine anion can give chlorine gas at the anode by losing 2 electrons. This means the stoichiometry is 2 here, here 1. We need 2 moles of chloride to get 1 mole of chlorine gas. Also, we need 2 mole of electrons. This means 2 times Faraday. 1 Faraday is equal to 96,485 coulomb per mole. I am approximately taking it as 96,500 coulomb per mole just to do the calculation easily. Now, we have determined that for 1 mole of chlorine gas, it is 2 Faraday, and therefore, to produce 0.1 mole of chlorine gas, what would be the charge required? 2 times 96,500 times 0.1 mole divided by 1 mole. This is mole, this is coulomb per mole, and therefore all these things will cancel out. We can write this one as 2 times 9650 coulomb, because this is 1 by 10, isn't it? So that's the charge we require to get 0.1 mole of chlorine gas. Now we know that number of coulombs charge is equal to current times time, and therefore time we can calculate. Here the number of coulombs required is 2 times 9650 divided by current is 3 amperes. We need the final answer in minutes, and therefore we are dividing it by 60. Again 1 0 we can cut down, and this is 3, and this means that 965 divided by 9, that will be 107.2. The closest answer we have is 110 minutes, and therefore option 4 is correct. The number of Faradays required to produce 20 gram of calcium from molten calcium chloride is how much? Atomic mass of calcium is given. First of all, let us understand what is 1 Faraday. Charge of 1 mole of electron is equal to 1 Faraday. Charge of 1 electron is equal to 1.6022 times 10 to the power minus 19 coulomb. This value multiplied by Avogadro number 6.022 times 10 to the power 23 per mole is what 1 Faraday is. This is equal to 96,485 coulomb per mole, that is 1 Faraday. What is the reaction given here? Molten calcium chloride undergoes electrolysis and we get calcium 2 plus and Cl minus. Calcium 2 plus we will get at the cathode and Cl minus we will get at the anode. Reduction happens at the cathode, anodic oxidation, cathodic reduction. This is something you already know. Calcium 2 plus gains 2 electrons and becomes calcium. The reaction happening at anode is Cl minus ion gives the chlorine gas and loses 2 electrons. Now, what is important thing that we need to understand here is the stoichiometric moles. To get 1 mole of calcium, we require 2 mole of electrons if we have 1 mole of Ca2 plus. That's the important thing to understand here. 2 mole of electron means 2 Faraday. So what is the weight if it is 1 mole of calcium? We know that number of moles equal to mass divided by molar mass. In this case we have to use atomic mass because we are talking about calcium. So 1 mole equal to mass divided by 40 gram per mole, and therefore the weight or mass is 40 gram. So 1 mole of calcium is equal to 40 gram, that is equal to 2 mole of electrons, and that is equal to 2 Faraday. Now the question here says that to produce 20 gram of calcium, that means half of it, half a mole of calcium is equal to 20 gram, that is equal to 1 mole of electron, that will be equal to 1 Faraday. Therefore option 4 is correct. What is the value of E0 cell when Fe3 plus becomes Fe0? If Fe3 plus is becoming Fe0, That means it requires 3 moles of electrons, isn't it? It has to gain 3 moles of electrons so that it can become Fe0. So this is reduction. So here we need to figure out what is the reduction potential when Fe3 plus becomes Fe0. What is given is Fe3 plus becoming Fe2 plus, that requires 1 mole of electrons, and it is also given when Fe2 plus becomes Fe0, that requires 2 moles of electrons. So let us say this is delta G naught 3. So therefore this is delta G naught 1 and this one is delta G 2 naught. So this means this is a sum of these two values, and we know that delta G standard is equal to minus NF E naught of the cell. So where N is the number of moles of electrons, so this is 3 moles of electrons, and F is the Faraday constant, and E cell standard is the reduction potential. So therefore this will be minus 3 times Faraday constant E3 standard, that is equal to minus 1 times Faraday constant times E1 standard minus 2 times Faraday constant E2 standard, and therefore that will be equal to minus 1 times Faraday constant times E1 standard is given as 0.77 volt and minus 2 times Faraday constant times and E2 standard is given as minus 0.44 volt. So this minus and this minus would become plus. So therefore this will be equal to minus 3 times Faraday constant times E naught 3 is equal to minus 0.77 volt times Faraday constant plus 0.88 volt times Faraday constant. Faraday constant is common, therefore we can cancel that. Therefore minus 3 E3 standard is equal to 0.11 volt. Therefore E3 standard is equal to minus 0.11 volt divided by 3. We can't divide 1 by 3. So 0. 11 by 3 is 3 times 3 is 9. So 3 remaining 2. We can't divide once again. Put a 0. It would become 20. So 6 times 3 is 18. Therefore 6 remaining 2. So this will be keep going. Therefore this will be equal to minus 0.04 volt. Therefore E3 standard is equal to minus 0.04 volt. So this means option A is correct.